So the first thing I want to go over is basically what a chemical reaction is. Okay, so a chemical reaction is a rearrangement of the molecules. Okay, so I'm sorry, it's a rearrangement of atoms. Okay, so in this case, we have carbon bonded to hydrogen, and we have oxygen bonded to oxygen. However, over here on the other side, we have carbon bonded to oxygen, and we have oxygen bonded to hydrogen. Okay? So in this case, we're breaking the bonds. On one side, we break bonds. And on the other side, we make bonds. Okay? Does that make sense? Yeah, Dr. Clark, that totally makes sense. Thank you.
It makes sense.
You're welcome. I'm glad I could help. Okay.
I didn't know the cat of a Disney movie was in your classroom.
Yes, the cat from a Disney movie is indeed in my classroom. Hold on, I've got to get my coffee real quick out of my goat mug. Okay. So the rearrangement of atoms is based on the movement of electrons. So on the movement, which by the way, MVMT is the abbreviation for movement. Movement of electrons. Okay. More specifically, valence electrons. Okay. Now, some ways we can recognize a chemical reaction, which we have already focused on chemical. We already have kind of talked about this a little bit. Is a couple of different ways. First, the first and easiest way to recognize a chemical reaction is a color change. So in this case, we have something that's clear, but it's becoming white. This one's my personal favorite, and if we were in class, I would do this for you. Actually, I don't think I can because I don't think I have everything I need. But this one goes from two clear liquids to a yellow solid. Okay, and that's what these are. These kind of cloud-looking things are actually solids floating in liquid. Oh, okay, to yellow solid. Okay, so color change is one form of a chemical reaction, and the formation of a solid is another. And if we were to look back at our reaction, it's kind of hard to see, but down here on the bottom, we actually have some copper, this really dark spot right down here at the bottom. So we are forming a solid from another solid. Okay. Let me change. I've got my notes on one side of the table and the slides on the other. One of the funnest ways we know a chemical reaction is happening is with bubbles. So bubble formation is a way we can determine if a chemical reaction is happening. And the word for bubble formation is effervescence. Okay, like when you say somebody has an effervescent personality, you mean what you're saying is they're bubbly. Okay, I just think effervescence is a cool word. Because what's really going on is you're forming a gas. Right? And that's an indication of a chemical reaction because you're changing from one state of matter to another state of matter. Now, if you have any questions as we go on, please do not hesitate to stop me. Okay. Another particular fun one is there's a temperature change. When there is a temperature change, there, like if we see right here, okay, there typically, that's an indicator of a chemical reaction. It is not always an indicator of a chemical reaction, but it usually is. And then of course, anytime we see a flame, that indicates a chemical reaction. Okay, and RXN is the abbreviation for chemical reaction. Okay. Now, speaking of chemical reactions, we want to kind of talk about what the parts of a chemical reaction are. This arrow right here is called the yields arrow. Sometimes it's called make, like we would read it as methane reacts with oxygen to make carbon dioxide and water. Because these little plus signs imply that we're adding those two ingredients together. So if we think about a recipe, the reactants are the ingredients. The products, well, pretty much is the product. The finished product is probably a better way to say it. Okay. So this little plus sign implies that these two things are reacting together. This plus sign over here implies that these things are both created here. Okay. The yields arrow always points to the products. There are some weird looking yields arrows, but we're not going to get into those. We're just going to deal with the single direction yields arrows. Okay, so this represents the symbols. And this represents the names. So the top part would be how we write it out in a sentence, whereas the symbols are how we write it out symbolically, so we don't have to write this very long methane reacts with oxygen to produce carbon dioxide and water. Any questions so far? Okay. Oh, goodness. Let's see, is that just one page? That is just one page. Excellent. Now, here's how a chemical reaction works. A chemical reaction, like I said, is just a rearrangement of elements. So we have, on this side, we have 1 carbon and 4 hydrogens. Okay? Right now they're together. And what I've done is I've broken up the reactants. Remember, these are reactants. Okay? And I've broken this oxygen into 2 separate oxygens. I've broken up the methane into 5 separate atoms. Now over here, I have the products. And what's happening is the atoms are rearranged. So reactants rearrange into products. But over here, I'm showing that I still have 2 oxygens, 1 carbon. But when I count the atoms, we notice that on the reactant side, I have 1 carbon, 4 hydrogens, 2 oxygens. On the product side, I have 1 carbon, 2 hydrogens, 3 oxygens. So here's the trick. There is something called the law of conservation of matter. And what that is atoms are neither made or destroyed, or nor destroyed. Sorry, got to use proper grammar. In a chemical reaction. And that chemical reaction part is super important. So right now, it looks like I'm getting rid of 2 hydrogens. It looks like I'm spontaneously making an oxygen. And if we count the atoms up here, we can see that. However, that doesn't happen. So this reaction is not what we call balanced, because the number of atoms on one side of the reaction must equal the number of atoms on the other side of the reaction. Okay, so, which brings us to this reaction. So if I go back and look here, I moved this too soon. I know I have 4 hydrogens. Over here, I only have 2, which means those other 2 hydrogens must have made an additional water. So those 2 hydrogens made an additional water. Now that gives me 2 oxygens or it gives, I'm sorry, it gives me 4 oxygens on the product side, which means I started with 4 oxygens on the reactant side. Now, since oxygen only comes in this O2 format, I must have had 2 O2s. Okay, so I've got these 2 oxygens coming together. And I have these 2 oxygens forming water. So now I have 4 oxygens on my reactant side. Now, of course, my carbon is fine, and my hydrogens are now fine. Since I have 2 oxygens here, I put a 2 right in front of the oxygen recipe. Okay, and what this means is that I have 1 methane and 2 oxygen molecules. And that forms 1 carbon dioxide molecule and 2 water molecules. So now this particular equation is balanced because if I count everything, it adds up on both sides. So I've got 1, 2, 3, 4. Over here, I have 1, 2, 3, 4. So my hydrogens are balanced. Over here, I have 1, 2, 3, 4. And on my product side, I have 1, 2, 3, 4. So my oxygens are balanced. And of course, I only have 1 carbon on each side. So this represents that atoms are neither created nor destroyed, which is super positive for us.
I have a question.
I have an answer.
Okay, so we did this in Hunley's class.
Okay.
He kind of showed us a different way. Is it okay if we do it that way?
Oh, yeah. We're not balancing reactions right now.
Oh, okay.
We just want to talk about how reactions are used up. We're going to balance reactions in another week or so.
Okay.
Okay. So you can balance them in whatever way makes sense to you. It does not personally affect me as long as it is correct.
Okay, sounds good.
Yeah.
Also, since you're teaching live today,
Yeah.
on the agenda it says take notes on the chemical reactions things. Is that what you're doing here?
That's what I'm doing here, yes. I'm going to
Okay.
upload this video to YouTube because
Okay.
honestly, I didn't have time to make the video. Because I had things to do this weekend, so I didn't have time to make the video like I usually do. Plus, I honestly miss teaching live and interacting with you all. So if this works, that's great. If it doesn't work, let me know, and we'll go back to me just providing a video. Okay. Now, here is something I want you to know about. We're not going to focus on too much. These symbols right here, what they do is they represent what state of matter the product or reactant is in, and they're pretty logical. S stands for solid, L stands for liquid, G stands for gas. However, the one that typically gives kids trouble, and when I say kids, I mean students, it gives even graduate students trouble sometimes, is this AQ. AQ stands for aqueous. And what that means is it's dissolved in water. Okay? Not everything dissolves in water, so the stuff that does, we have to specify that, oh, this is dissolved in water. And the thing is, if we look down here at solid potassium, we see the little S. Water is a liquid, we see the little L. It produces hydrogen gas, which is G, and it produces potassium hydroxide dissolved in water, which is AQ. Now, here's the trick. The reason we include these is because if we have this, okay, if potassium is a liquid, there won't be a reaction. Okay, so just because potassium reacts with water does not mean it always reacts with water based on its state of matter. So I will include these in reactions, but if you don't include them, I'm not going to count off for it or anything like that, because you guys may or may not be familiar with all of it there. And if I want you to include it, I will tell you specifically to include it. Okay? Now, that ends the lecture portion of the day.